In the previous video, we had discussed the factors which govern Manning's roughness coefficient. In this video, we are going to look at a particular example where in a given cross-section, we may have different bed materials lining different parts of the channel bed and how we can compute what is called a composite roughness coefficient or an equivalent roughness coefficient. So here in this cross section we can see that a part of the channel bed consists of bedrock, which would have a certain value of the roughness coefficient. Then there is this middle part which consists of sand, and we have a third part which is consisting of gravel and cobbles. Let N1, N2 and N3 denote the corresponding Manning's roughness coefficient, and the corresponding wetted perimeters are denoted by P1, so this corresponds to P1, the middle part corresponds to P2, and the last part corresponds to wetted perimeter P3. Their areas are denoted by A1, A2 and A3 respectively. So this area is A3, this is A1, and the middle part is A2. If we have channel conditions such as this, then what would be the equivalent roughness coefficient? So for each of these sections, we can write the hydraulic radius. So R1 is A1 by P1, R2 is A2 by P2, and R3 is A3 by P3. And we know that if we add the areas, we get the total area of the channel, which is A, and we are interested in the one-dimensional velocity along the channel, which we have denoted by V. So therefore, velocity at each of these sections, V1, V2 and V3 are equal, and we write that to be equal to the velocity, average velocity V. Also, at a given cross section, the slope, the longitudinal slope of the channel does not change, and therefore the slope is also same in each of these three sections, which we can write from Manning's equation in terms of the equivalent roughness coefficient N. Now, when we write Manning's equation for each of these three subsections and we rearrange the terms a little bit, then we can write each area in terms of its weighted perimeter as well as the total area and the total weighted perimeter and the equivalent roughness height and the equivalent roughness coefficient. We also know that the sum of all these three areas would give the total area A. So when we use that and rearrange the terms a little bit one more time, then we get the expression for equivalent Manning's roughness coefficient N, which is written in terms of the individual weighted perimeters as well as the total weighted perimeter. So the total weighted perimeter P is nothing but the sum of these individual weighted perimeters P1 plus P2 plus P3. Alright, let's solve a problem to make this concept a little more clear. So here we are talking about an earthen trapezoidal channel whose roughness coefficient, this is for the earthen material, is given to us, the bottom width is given to us, and the side slopes are also given to us. The depth of flow is also given as 1.1 meters. However, if this channel is an earthen channel, so this is the channel cross section. So this is earthen channel, trapezoidal. Side slopes are typically represented by the horizontal to vertical ratio, which is 1:m. Here it is 1:1.5. The depth of flow is denoted by Y, and the bed width is denoted by B. So if we have this trapezoidal channel made of earthen material, there would be seepage along the sides as well as along the bed. And to remedy such excess seepage, it is proposed that the lines be channeled with smooth concrete that has a different roughness coefficient. So it is proposed to line these two sides with concrete n equal to 0.012, whereas the bed bottom width continues to remain with earthen material whose roughness is 0.025. If we adopt such lining, then what would be the equivalent roughness coefficient? That's the question here. So we denote for the bed, we use the subscript 1, and for the sides we use 2 and 3. So for the bed we have N1 noted, the P1 is 5 meters. By using this horizontal to vertical ratio, we can calculate the weighted perimeter P2 and P3. So this is P1, this is P1, and this is P2, and this is P3. Right? So P2 and P3, we can use the horizontal to vertical ratio to calculate from geometry. P2 is equal to P3, and that comes out to be 1.983 meters. N2 and N3 are given to us as 0.012. Then we use this formula that we have derived here, plug in all the values of the individual weighted perimeters as well as the individual roughness coefficients, and this gives us an equivalent roughness of 0.0198. So it's a little lesser than the earthen material. There is a subpart of this question, and that becomes a homework for you. What is the new equivalent roughness if instead of the sides, if only the bed is lined? So what would be the equivalent roughness then? If only the bottom is lined with smooth concrete. So this sort of concludes our discussion on Manning's equation. One aspect that I need you to note here is that Manning's equation is valid for rough turbulent flows. It so happens that in nature, in most open channel flow that we encounter in reality, rough turbulent flow is what we expect. But therefore, when we are relating Manning's roughness coefficient with the Darcy friction factor F, you need to keep in mind that it is valid only for rough turbulent regimes. So in the next video, we are going to talk about how velocity distribution varies along the depth of the channel and so on. See you.